So now that we've looked at integration as area under a curve, and we've seen it kind of in general there, I want to look a little bit more closely at this idea of the constant of integration. We introduced it just at the end of our last lesson here, but you'll notice here I have three different functions, f, g, and h. E to the 2x, ln of x to the fourth plus 3x. And you'll notice the only difference there is the plus 5, the minus 11, and the plus 85. Okay? And this actually illustrates our point here. If I were to take the derivative of each of those, okay, I'd have to use the chain rule for the e to the 2x, so it'd be e to the 2x times the derivative of 2x. And then the derivative of the natural log. Do you guys remember the rule for derivative of natural log?
It's the derivative of the function divided by function.
All right, yeah, if you have that function inside the natural log, it's the derivative of that function over the original function. Okay, so 4x cubed over x to the fourth. And then plus 3 plus 0. Now the 0 comes on all of these. Okay? And of course we can reduce this and you'll get what we have down here, the 4 over x. Okay? But notice those derivatives are all the same. If we were to take the integral, the indefinite integral, or antiderivative, we would express it as capital F of x plus c. All right? Capital F of x out.
Why do you have to 0?
What, here?
Yeah.
I was just showing that for all three of those, the constant portion becomes a 0.
Oh, okay.
Okay, so
Oh,
yeah, on all three of those, that constant, when you take the derivative, is 0. So, because we recognize this, if we were taking the antiderivative of f, we would say it's capital F of x plus c. And that opens up the door for any vertical translation, because that's really what's going on here. When you add a plus c, it's a vertical translation of the function up or down. Okay. Now, one of the things that we can do as we start to learn a few rules is to consider derivatives of functions as we try to come up with rules for integrals. So this is kind of a nice help to start us, and you had a couple of these in the practice, that number 3 in the practice from the previous lesson there, where you were told to consider the derivative of this to try to find the integral. That's exactly what we're doing here. Okay, so if I found dy dx for e to the 2x plus 1, what would that derivative equal?
2e to the 2x.
Yeah.
2e to the 2x.
2e to the 2x plus 1. Okay? That exponent stays the same. But then I multiply by the derivative of the exponent. Okay? So, looking at the integral here, I almost have 2e to the 2x plus 1. So, if I had a 2e to the 2x plus 1, then the integral would equal e to the 2x plus 1, right? Because taking the derivative of this gets me here. So taking the integral of this would get me back to here, right?
No.
With a plus c.
Yeah.
Okay? I don't quite have that. However, let's say I had a 2 here. Okay? that integral would equal e to the 2x plus 1 plus c, right? However, am I allowed to just throw 2's in wherever I feel like it? No, okay. What could I do though?
Put one.
Yeah, no, you're absolutely right. What'd you say?
Put a half instead of a one, but then, yeah, I don't know why that would work.
Well, yeah. I'm going to actually, instead of just multiplying by 2, I'm actually going to multiply by the identity 1. Alright, we're allowed to multiply by 1. It doesn't change the value, right? But I'm going to multiply by 1 in the form of multiplying by 2 and multiplying by a half. That would equal 1, but notice now in the integral I have what I need, and outside of the integral I just have this 1/2. So the integral of e to the 2x plus 1, after I put the 1/2 and the 2 in there, is going to be 1/2 e to the 2x plus 1
Why can't you just put one, like,
plus e.
why can't you just leave it? 'Cause it's not, but I don't really understand.
Well, it actually has to do, it's a similar property to what we saw with derivatives of functions. If you remember, when we took the derivative of a function times some constant, we were able to take just the derivative of the constant and then multiply it by, or of the function, and then multiply it by the constant afterwards, right? Well, the same rule applies here for integrals. If I have the integral of a constant times a function,
But you don't. This is just e to the 2x plus 1.
you're right, okay? We'll see the full development here. I can pull that constant out and make that c times the integral of f of x dx. Let's see how that's happening here. I don't initially have an e to the 2x plus 1. I need a 2e to the 2x plus 1. Okay? So, in there, I'm doing 1/2 times 2, e to the 2x plus 1. Okay? I'm allowed to multiply by 1 whenever I feel like. Okay? So now what I'm doing is I'm viewing this as that function, okay, and the 1/2 is the constant. So I can pull that constant out in front of the integral, okay.
The other part just goes back to what it was before.
Yeah, the other part I know because I just did the derivative. I know that the integral of 2e to the 2x plus 1 is going to be e to the 2x plus 1. And the 1/2 is just there, okay, because we needed it to balance out the 2. Okay. This is going to take a little bit of time to get used to doing, all right? We've done a lot of derivatives. It's going to take a little bit of time. So don't get frustrated with it. It's just we just got to take it one at a time. And that's why we're starting with this style of problem first. Okay? So let's work through another one here. If y is 2x plus 1 to the 4th, dy dx would equal what? 4 times 2x
Plus 1 to the third times 2 times 2.
times 2. Okay. So, if I simplify a little bit, it's 8 times 2x plus 1 to the third. So that's what the derivative of 2x plus 1 to the 4th is. So now, if I want to take the integral of 2x plus 1 to the third,
Oh.
what do you think I should do?
So you should multiply the integral times 8, and then multiply the outside, I don't know if that makes sense, but multiply the outside times 1/8.
Yeah, that's right.
You do the same on both sides.
Yeah, I'm multiplying by 1, it's just part of the 1 is inside the integral and part of the 1 is outside the integral. Okay, so there's my 8 times 1/8. Now I can say that the integral is 1/8 times, what's the integral of 8 times 2x plus 1 to the third?
2x plus 1 to the fourth.
Yeah, 2x plus 1 to the fourth plus c. Okay? So, taking the derivative gets us from 2x plus 1 to the fourth down to an 8 times 2x plus 1 to the third. So, if I'm taking the integral of 8 times 2x plus 1 to the third, that's going to take me back to 2x plus 1 to the fourth. Alright? And again, you can see this as an inverse relationship here. Here we have 2x plus 1 to the fourth. Here we have 8 times 2x plus 1 to the third. If I am taking the derivative of this, it goes that way. If I'm taking the antiderivative, it's going to take me back here with a plus c. Okay?
But you're not getting the original function. You are, but at the same time you're not. Because in order to make the beginning part 1, you'd have to multiply by 8, which would then you'd be taking the derivative.
Well, notice, I'm talking about just the 8 times the 2x plus 1 cubed. Okay? Yes, we end up with 1/8, but that's not inside the integral. The integral itself equals the 2x plus 1 to the fourth. Yes, we do end up with a constant there. Alright? Alright? Now, this brings us to our first two rules, okay, rules for integration. One, we already kind of derived yesterday in the homework, okay, from yesterday. The other one is actually just a variation of the second one, okay? So, notice here, we're going to look at constant and what we call power functions, or you could think of them as polynomials, all right? Polynomials. This second part here is what we saw already as we were going over the homework from yesterday. If I am taking the integral of x to some power, then I am going to add 1 to the power and divide by the new power. And then there's a plus c at the end. Okay, so that's why we got the integral of x squared is x cubed over 3. Add 1 to the power, divide by the new power. You'll notice there it says, though, that n cannot equal -1. Do you guys wonder why? It would make the bottom 0. N cannot be -1 because if I took the integral of x to -1 and tried to use this rule,
When plus 1 equal to 0.
yeah, when I add 1, it ends up to 0, and I'm dividing by -1 plus 1.
That's undefined.
So x is 0 over 0, yep, can't do that. There's actually a different rule for that. which we'll learn here actually later on.
Hey, wouldn't that just be C though?
What?
If you're doing the integral of x to the power -1, wouldn't you just have C?
No, because it'd be undefined.
It'd be undefined because it's over 0.
No, it would be undefined, like theoretically, but at the same time, it's like it's in when you take a derivative, you take a power down. When you take the antiderivative, you go a power up, regardless of the rule. Wouldn't it just be x to the 0, which is 1? So you just get the the constant.
Well, again, you would have undefined plus C. So if it's undefined plus C, that's undefined. So I know that one's a little bit odd. And actually, I'll give you the rule right now. If n equals -1, then the integral of x and -1 dx is actually the natural log of the absolute value of x. That's the rule right there. Okay? And we're not going to get into why here in SL. If you do AP, we'll look at it more closely. That's just a rule you'll have to memorize. Okay? Now, we skipped that first one there for k being a constant. If we have the integral of a constant, all right, the integral of a constant, it says is kx plus c. All right, well, let's look at that. If I looked at it in terms of the second function, all right, the constant k, I could rewrite as k times x to what power? No, because that would be kx squared, not just k.
Ask a question.
What power would I have to put here with the x to make it equal just a k? 0. There you go. If x were to the 0 power, that's just 1, right? Okay. Well, let's use that with the rule that we just learned, our power rule. Okay, I'd have k times x to the 0 plus 1 over 0 plus 1, right? Well, that's just kx over 1, or kx. And then I'd put the plus c. So the constant term is actually kind of a special case of the power rule that we just looked at, okay? Okay? So a couple of basic rules we're going to start with here, and we are on our way in integration, okay? Now, we're going to practice with a few of these here, and if you don't quite finish everything, we can finish for homework.